this. So this series of lectures is part of the lectures already given by Anupam. So he had given 3 lectures on introduction to elliptic curves, and second part I'm going to discuss the Selmer groups. So here are the contents. First, so there are so Selmer groups can be defined indirectly using group cohomology of basically Galois cohomology of elliptic curves, but it's sometimes useful to also have its a geometric interpretation of elements of the Selmer group. And for that, I'll also recall principal homogeneous spaces. I will mostly stick to the things which I need for these lectures. So I will be discussing only elliptic curves in the context of elliptic curves. Even for group cohomology, I will be looking at only 0th and 1st cohomology groups. And after defining these 2 objects, we'll go to, I will recall the definition of Tate-Seprovich group of elliptic curves, then Selmer groups. In Selmer groups, this topic, there will be 3 subtopics mentioned here. First, all the proof of finiteness of n Selmer group for a positive integer n, and then as a consequence, we'll get weak model theorem. I'll also briefly sketch or discuss Kumar pairing for elliptic curves. And in the final topic, which will be even more sketchy, and so in this section, I will recall Bloch-Kato Selmer group and its relation with. So again, although I will define it in slight generality, but mostly I will be stating results related to Selmer group. I'll basically compare it in the Bloch-Kato Selmer group of elliptic curve with the usual Selmer group of elliptic curve. So it's like this section is like kind of illustration of what general objects appears. Here are these 2 reference books. First one is the Arithmetic of Elliptic Curves by Silverman, and second one is again Elliptic Curve by Milne. These are the 2 main books. There will be so most of the things I will be covering here are from this book. These 2 books. I will also use the notations and terminologies from these 2 books. And there will be few extra topics also. Time to time, I will mention from where I am taking them. So let us begin with the definition and basics of group cohomology. These are the key ingredients in the definition of Selmer group. So we begin with the cohomology of finite groups. So let G be a finite group, and a G module M together with an action of G, that is a map from G cross M to M, satisfy these properties, that sigma of M plus M prime equal to sigma M plus sigma M prime, and sigma tau M is equal to sigma tau M for all sigma comma tau belong to G and M belong to capital M, and identity fixes all the M. So if these 3 properties are satisfied for this map from G cross M to M, then we say M is a G module. Equivalently, we have a group homomorphism from G to the group of automorphisms of M. So the example which we are interested in this lectures is coming from elliptic curves. So let L be a finite Galois extension of a field K, and G be its Galois group. So G is the Galois group of L over K. Let E be an elliptic curve over K. Then EL is a G module via the coordinate y action. So this is an example which we will be looking at throughout these lectures. Here next we call the 0th cohomology group of M. So let M be a G module. Then we take all those elements in M which are fixed by all the elements of G. So this group is called H, denoted by H naught G comma M, and this is called the 0th cohomology group of M. Here again with the above example, if we take the points of E over L and apply and take the fixed point by G, we actually get EK. So next is about the first cohomology group. So here the first cohomology group of a G module M consists of what are called classes of cross homomorphisms. So what is a cross homomorphism? So it is a function from G to M, and it satisfies f of sigma tau equal to f of sigma plus sigma f tau for every sigma comma tau belong to G. So here f tau is an element of M, and then we apply sigma on f tau. Also, there are elements, special elements called principal cross homomorphisms, and these are defined as f sigma equal to sigma m minus m for a fixed m belong to capital M. So then set of cross homomorphism is a group under the pointwise addition of functions, and principal cross homomorphism form a subgroup. So we can define this quotient. So H1 of G comma M, the first cohomology group of G comma M, is defined as the group of cross homomorphism modulo the group of principal cross homomorphisms. Next, I would like to note down here that if G acts on M trivially, then H1 G comma M is nothing but home of G comma M. So this is just immediate from the definition of the cross homomorphism here. So this little point is going to be useful when we give a proof of weak model wave theorem, and there it will be act as a simplifying thing. So to simplify our proof, so maybe we should note down it, and so that we can recall it later on. Next is what is called a connecting homomorphism. So this is again we will be using several times throughout this lecture. So I thought it's better to have a definition written down, have definition of this connecting homomorphism written down here. So how do we define it? So let M to N to P be a, sorry. Yeah. So M to N to P be an exact sequence of G module. Then we want to define a homomorphism from H naught of. So we want to define a homomorphism from H naught of G comma P to H1 of G comma M. This will be called connecting homomorphism. So for this, what we do, take an element of H naught of P. So P small p belong to H naught of P here. And what we do, we pull back. So via this psi, so this N to P we have map psi. If you take fixed point, then it may not be surjective, but without taking fixed point, psi is surjective, so we pull it back. So let small n be such an element, and the image is small p. Then we can define delta p of. So what we notice here is that if you apply the function psi on sigma n minus n, then this is 0, and therefore this sigma n minus n is in the kernel of psi, and in delta p of sigma equal to m sigma. So this is a well-defined function from h naught of G comma P to h1 of G comma P, and this is called a connecting homomorphism from h naught to h1. Once we have this definition of connecting homomorphism, this next proposition is routine checking. So given an exact sequence M to N to P of G modules, we have a long exact sequence of groups. So first we have H naught of M, N, and P respectively, and then H1 of M, N, and P. After that, also it goes higher cohomology groups, although we need it. So I have written here only up to first cohomology group, so that is what we need later on. And here delta is the connecting homomorphism. So this is what it connects, zeroth and first cohomology groups. One more, two more maps we need, and they're called inflation and restriction homomorphisms. So what are they? So given a cross homomorphism from G to M, we can restrict it to H, and it immediately gives us a cross homomorphism on H, from H to M. So this is a group homomorphism, and this homomorphism is called a restriction homomorphism. Another map is called inflation homomorphism. So how it is defined? So given a normal subgroup of G, let H be such a normal subgroup, and M be a G module, then M fixed by H. So H naught of H comma M becomes a G mod H module. So then if you have a cross homomorphism from G mod H to M fixed by H, we can define a cross homomorphism from G to MH, and then we can include MH inside M. So we get a cross homomorphism from G to M. So this gives us a, this will give us a map from this H1 G mod M, G mod H, comma M fixed by H to H1 G, comma M. This is called inflation homomorphism, and we have a Z sequence here. Proof is again routine and easy to do. This sequence is also called inflation restriction sequence, and so what it does, the first map is the inflation map, and then second one is the restriction map. It says that the kernel of restriction is precisely the image of inflation. So, and its image of restriction is actually inside again. So this I have not explained, but if you have just like we had an action of G mod H on M fixed by H, we will have an action of G mod H on this H1 H comma M also, and from here, yeah. So this. So, and it's this proposition says that image of this restriction lands inside this set of group of fixed point by G mod H. Yeah, so these were all about cohomology of finite groups. We will need cohomology of infinite groups, but special kind of infinite groups, the groups which are also Galois groups. They are actually for finite groups, so they have topology on them. So let me just briefly recall that also. So let K be we will be mostly considering only perfect fields in these lectures. So let K be a perfect field, and let K bar be an algebraic closure of K. And let J subset of K bar be a normal extension of K, not necessarily finite. Then and let us consider the Galois group of, so Gal J comma K be the Galois group of J over K. This is a profinite group, so actually a compact topological group, and from Galois theory we have Galois group of J comma K is the inverse limit of Galois group of finite Galois extensions of K. And mostly except in the last part of the lecture, we will be looking at discrete modules over such Galois groups. So let me take a discrete, let M be a discrete Galois, so it should be actually GAL, discrete Galois G of J comma K module. That is, so what it means that corresponding maps of G modules are continuous. That's what it means. Another way to define a discrete G module is, or Galois module is, that M is union of these fixed elements of M by open subgroups of open subgroup of Gal of J comma K. So these are two equivalent way to see them. Also, another way to see such modules are by demanding that stabilizer of every element in M is an open subgroup of G of. So sometime I will write gal of J comma K. Sometime I will just write G of J comma K. It's usually something I forget, right? Gal group of J comma K. So but both will mean same thing. So equivalently, what M is a discrete module if stabilizer of every element in M is an open subgroup of Galois group of J comma K. So these are a few equivalent way of defining discrete modules over such groups. Here are examples. So if again this is the example which we are interested in, so let E be an elliptic curve over K and J be then for any, so we had J is the same extension of K. So then EJ is a discrete discrete module over Galois group of J over K. In fact, what we see here is that E of J is actually union of E of L, where is our finite extensions of K. So from here we see that E of J is actually a discrete module over this Galois group. Another module which is also a subgroup of EJ is the what we call the torsion subgroup of E, but not over K, but the bigger extension J. Then EJ torsion subgroup is again a discrete submodule of EJ. So yeah, these are the two examples which will appear again and again. Now, so let me now define. So earlier we had defined group homologies of finite groups. So let me now define or mention how to define group homologies for infinite. Define Galois homology groups. So for an infinite Galois group, gal J comma K and a discrete module over it. Let's say M is such a M be such module. Then H1 G comma M is defined as so earlier we took all cross homomorphisms modulo principal cross homomorphisms. Now we take only continuous. So we have a topology on G and topology on M. So instead of all cross homomorphisms, we just take continuous cross homomorphisms. Go modulo principal cross homomorphisms. Another equivalent way to define cohomology, group cohomology over such groups, profinite groups is by taking this direct limit under inflation map. So we remember we had this inflation restriction sequence. So this is a, if I have a extension, if I have a tower of extension, then this will be actually inside. So if so this will be inside H1 of Galois group of L prime over K, comma M, and then we take the same group G here. I'm not writing the full thing. If L prime contains L from that inflation restriction sequence, and we take this direct limit with respect to this inflation maps. If M is a discrete module over the Galois group, then these two definitions, either you define it using continuous cross homomorphisms or define using this limit, both are essentially the same. I'd like to mention here that since this M is a discrete module, this stabilizer of M is a open subgroup, and therefore actually it should be G here. See here. J comma K. So it's a actually open subgroup of Galois group of J comma K for every M belong to capital M. And in fact, that just says that maps of this kind are actually always continuous. So we don't have to go more to principal continuous principal cross homomorphisms. They will anyway inside. Here is a proposition which actually says that, so if you have a discrete G module discrete module over a Galois group of j comma k. So this should be j comma k, and then this h1 of Galois group of j comma k comma m is actually torsion torsion group. So how do we see it? It's in something important and interesting even for our purpose. We'll see it later on when we define various homology groups associated with elliptic curves. So how do we see it? We see it. We just use two things. First, for infinite Galois group, the homology is defined using the direct limit. So it's enough to prove it that these groups are torsion. And for finite group, proof is rather easy. Simple. Little bit of calculation gives us that yeah. So I've done the computation here, which essentially says that if you have order of this group G, if I have a J over K is a finite extension, then if n is the order of the Galois group of J over K, then n actually kills this H1. So that's what is the proof. Yeah. So these were things which we would need for. These were the things from group homology which we will need for purpose for defining Selmer groups and Tate subgroups group and other objects. So next is, as I said, it's sometimes useful to have a geometric interpretation of elements of Selmer groups also. So let me now move to next topic called the principal homogeneous spaces of elliptic curves. But before I go to the principal homogeneous space of elliptic curves, let's just look at the principal homogeneous spaces of sets. So then we will go to elliptic curves. So let A be an abelian group, then a right A set. So basically this means that A acts on W from right. So a right A set is called a principal homogeneous space for A if first of all W is non-empty and the map. So we have this map W comma A going to W comma W plus A is a bijection. So first of all, because W is an A set, we have such a map which satisfies all. Yes.
Can I interrupt?
Yes.
There is a question in the chat box. The question is, yeah. Okay, shall I read it out for you?
No, I look at it. Oh, so okay. Yes. So yeah, did I? So whenever I'm talking about G mod H, then we need N to be normal also. That's what I think the question is.
Yeah.
It's not just if I want to talk about G mod H, then not just open, but we would need it to be normal also. Yeah. So here, when I say W is an A set, basically means that it's A acts on W. So this condition that this map is actually in a bijection also can be restated by saying that G acts on A acts on W freely and transitively. But sometime we'll see later on, at least for looking at if we are looking at principal homogeneous spaces of elliptic curves, it's also useful to define it in this particular way. In fact, some of the propositions which I'm going to state will be much easier if we just define it that A acts on W freely and transitively. But anyway, let us have this particular definition. We follow this. So, yeah. So actually, this map with bijection immediately implies that given two elements in W, W1 and W2, there is a unique A belong to capital A such that W1 plus A equal to W. So this we will be using several times. And what is a morphism of principal homogeneous space? It's a morphism which also preserves this A action. So it's a function which preserves an A action. Here are a few examples. If I have a abelian group A, then A makes a principal homogeneous space via this usual, because A is an group. So we have such a map here that makes A into a principal homogeneous space. This is actually called a trivial principal homogeneous space over A. For a field K, the affine line is an example of principal homogeneous space. There is a proposition which is very useful for us. So what is this? So let W and W prime be two principal homogeneous space for A. Then for any element W1 belong to capital W and W2 belong to W prime. There, maybe I should have used the notation W1, W and W prime. But anyway, the proposition says that there exists a unique morphism phi from W2. So when I say morphism, I mean the morphism of a principal homogeneous space. So there is a unique morphism theta from W to W prime such that theta of W1 equal to W. Moreover, it says that every morphism between two principal homogeneous spaces are actually an isomorphism. So this anyway should be immediate if we look at the other definition which I said in terms of free and transitive access. Yeah, let me just, using our definition, let me just briefly say why it is true. And so we want to define a function. First of all, we want to define a function from I to, we want to define a function from W to W prime. So how do we do it? So we use this property. So we had this property here, and that given two element W1 and W2, there exists a unique element A such that it takes W1 plus A equal to W. That's what we will use. So given an element small W belong to capital W, we have a unique A such that this happens W equal to W1 plus A, and therefore we can, so using that we can define phi a function. We can define, actually I should have the notation theta here. It's actually theta here. This notation. So yeah, so we can define it theta to be sending W to W2 plus A, and immediately we see that it satisfies this condition which we want, that that W1 should go to W2. Now for uniqueness, what we need to notice that if I have any such morphism psi, then because it's a morphism of principal homogeneous space, it will satisfy psi of W1 plus A equal to psi of W1 outside A, and that is equal to W2 plus A. So it just agrees with this function, and therefore we have only one such. So we just have to fix two element, and that will determine the morphism. Also, to see that all morphisms between principal homogeneous spaces are isomorphism, for we just use the uniqueness again, and both direction we have only one map which takes. So we can fix two elements, and then we have one map only which takes one element to another. The composition will be identity on both sides, and therefore both will be isomorphisms. Yes. So now, so again, if you apply this, so as I said, A is if I have a group A, then abelian group A, then A is also a principal homogeneous space. And if I have any other principal homogeneous space, because we know that there is always a given two elements, one from first space and another from second space, then we get a unique map which takes that one element to another. So in A, we have a special element identity, actually zero element, it's an abelian group. So it takes, we have a unique morphism of principal homogeneous space which takes identity to or 0 to W. We also notice here that from A to we have a morphism. We have a this function homomorphism which takes an element A to a morphism of principal homogeneous space taking W to W plus A. Okay, so these are two things you can note down. So next we come to our topic, that principal homogeneous spaces of elliptic curves. So now let E be an elliptic curve over a field K, and so I have a number field. I have a field K. Now I am later on I'll specialize it to number field case, but for now let's take a field K. And then a principal homogeneous space for E is a curve W over K together with a right action of E given by a map from W cross E to W. Such that again similar the way we define it for sets, we have this morphisms of algebraic varieties should be an isomorphism. Okay, so this definition is similar to what we had for sets. Only thing here is that here we demand morphisms to be not just any morphism, not just morphisms of sets or points, valued point, but also morphisms of algebraic varieties. So now it's immediate consequence of this definition that once we have, if we have a principal homogeneous space for an elliptic curve E, then if you take a field extension L over K, then there are two cases can occur. Either W has no point over L, or it's a, so you remember for principal homogeneous spaces of sets, we demanded that W should be non-empty. So if WL has no point, then anyway, it's not a principal homogeneous space. But if it has a point, then it's a principal homogeneous space of EL of sets. A morphism phi from W to W prime of a principal homogeneous space over E is a morphism of algebraic variety. So earlier we had morphisms of principal homogeneous spaces of sets, which were just maps of set which preserves AX. Here we have spaces, principal homogeneous spaces for elliptic curves. We demand it morphisms should also be morphisms of algebraic varieties. All the propositions which I stated for sets are also true here. So proposition which I stated earlier was for proposition 4. So that and its consequence applies to principal homogeneous spaces for elliptic curves. Also, in particular, this E cross E to E, and the addition of makes E a principal homogeneous space over E, and it's called trivial principal homogeneous space of E. Again, if W and W prime be principal homogeneous spaces of E, then for any small W belong to, so if you take a point K here and W prime another point, then there exists a unique morphism from W to W prime of principal homogeneous spaces, just like we had for sets, sending this W to W. Further, such a morphism is in fact an isomorphism. Also, we know that if you have a curve, then there exists an extension over which it will acquire a point. And once it acquires a point, then E is a principal homogeneous space and W is a principal homogeneous space. And we know that there is morphism, and such a morphism is also an isomorphism. So we get actually an isomorphism of from W to E. So once it has a point, then it becomes isomorphic to E. Over it. So over an extension, every principal homogeneous space of E becomes a trivial principal homogeneous space. Okay. Sometimes also we use a term that W splits over that extension. Just like sets, we have again given a point in E, K, we get an automorphism of W by this multiplication by P. And in fact, it can be shown that every automorphism of O over K is of this form for unique P belong to K, EK. So how do we classify all the principal homogeneous spaces of an elliptic curve. So this is where group cohomology comes. So the earlier topic and this topic, that's where these two meet together. So let W be a principal homogeneous space for E, capital W, and small w be an element in small w be an be an element of and be a point of this space over over a fixed algebraic closure K bar of K. So now I want to given a principal homogeneous space, I want to relate it with the group cohomology of certain group cohomology associated to elliptic curve. So how do we do it? So we have the action of this Calva group of K bar over K on the points of W. So given a point small w, we get sigma w. Again, this lands inside W of K bar. There exists a unique element F W sigma. So there is a unique element F of W sigma belong to EK bar. Once so remember, if you have two element in principal 2 points in principal homogeneous space W and W prime, then they differ. So there exists a unique element in the group such that W equal to W prime plus A. So that's what we are using here. So from there we get sigma W equal to W plus an element in points of elliptic curve over K bar. And what is nice about this FW sigma is that it satisfies the proper the definition of cross homomorphism. So we easily see that F of W sigma tau equal to FW sigma plus sigma of FW tau. Okay, so what we get here, that given a principal homogeneous space and element in that, we get a cross homomorphism from Galois group of K bar over K EK bar, the points of E over K bar. Yeah, sorry, there was some problem with my so I'm really sorry for this. Okay, so now so we had given an element W and a principal homogeneous space capital W, we get a cross homomorphism associated to it. And in fact, using the fact that the space itself splits over a finite extension, immediately see that actually this homomorphism is also continuous. So now we need to really see that this is independent of choice. So we want to associate a cross homomorphism to a principal homogeneous space, not just we want to get it independent of the chosen point, and that's also immediate. So only thing is that for that we have to go modulo the principal cross homomorphisms. So given two such points, we can again use the same property which we had used before, that there is always a point capital P which such that W and W prime differ by that. And so from there we see that these two cross homomorphisms FW and FW prime differ by A. So they differ by a principal cross homomorphism. So this the associated cross homomorphism is independent of the choice of this point W. So we can choose any one such point to define this cross homomorphism. We in fact also so we have now what we want to do, that we have one side we have, let me just write down here, or I have written it below. We have here one side we have set of all principal homogeneous spaces of E up to isomorphism. Another side we have this H1K of E. So what is this H1K? This is actually H1 of Galois group of Galois group of K bar over K, comma E of K bar. Okay, so these are this. So I think it's not visible here. Let me just write down slightly this side. So this is nothing but H1 of H1 of Galois group of K bar over K. Okay, so we have these two objects, and we want to, given a principal homogeneous space, we want to associate it to a cross homomorphism and other way around also. And that's what we have done here. First, we took a space and a point on that, and then we got a cross homomorphism, and then we showed that modulo. We saw that it's independent of choice of point, and once we go modulo principal elements in this. So now, in fact, for inject, so next we will in this theorem 5 we will show that this map is injective. But before showing injectivity, let us just show that what are the elements which goes to 0. So trivial which goes to 0 classes. So for that, suppose that this associated cross homomorphism is trivial. That is, this is equal to sigma p minus p for some point p in K bracket. Then what we get is that this W minus P actually belong to WK. So that just means that this space W splits over the field K itself. So that means W is a trivial trivial principal homogeneous space. And this shows that actually, although we have not, so there is no group, a priori there is no group structure on this, at least it shows that the only thing which goes to trivial element here are only thing which goes to trivial element here are precisely the trivial principal homogeneous space. Here also, of course, one also need to say that if two principal homogeneous spaces are isomorphic, then they go to same element or same class here in H1K. And for that, again, we use this definition that if sigma W is equal to W plus F sigma W, apply this isomorphism phi both side, apply this isomorphism phi both side, and from there it's immediate that the cross homomorphism associated to F associated to first homogeneous space and the second homogeneous space both are same. So this map is actually well defined, and only so we have injectivity not we have shown it, but at least we have what we have noticed is that elements which goes to 0 are precise is the trivial principal homogeneous space. Here is the main theorem of this section, which says that this function defining sending this spaces principal homogeneous spaces to elements in H1 is actually a bijection. So every element in the first homology group is associated to a it comes it's not just it's given element here, we got an element here, but the theorem says that we can given an element here in H1 we can get a principal homogeneous space also. So let me first quickly say that why quickly, so that it's a injective map. So let W and W prime be two principal homogeneous spaces of E over K. And now as we have already seen, we can use any point in W K bar to define the corresponding cross homomorphism. And suppose that the FW, the class of FW is equal to FW prime in H1K. So then, so we want to show that class of FW is equal to if this two happens, then actually this W and W primes are isomorphic. But let us first, just instead of saying the class, let us first see what happens if these two functions themselves are equal. And for that case, we in fact immediately get a little bit of calculation gives us that actually implies that. So first of all, these two things same implies that there is a point P belong to EK bar such that FW sigma equal to FW prime equal to sigma P minus P. So let us first, let me just write on this. So let us first suppose that FW equal to FW prime. And then first, okay, so first what we will do is that we will reduce this case to, by assuming reduce this case to the case where actually FW will be equal to FW prime, not just their classes. And for this is, that is what I have a little bit of calculation. Using this calculation I have shown here that, and once we have this two, and that FW is equal to W prime, and then remember we had this point, so we had a point W belong to capital W and W prime belong to capital W prime. So we get a function phi from the unique isomorphism phi from W to W prime over K bar with phi of W equal to W prime, and this phi actually in fact so this is happening over K bar because over K bar both are isomorphic to K. So this is happening over K bar, and then later on we actually show that by showing that this phi of sigma of x equal to sigma of phi x, we show that these 2 points actually we can choose over K itself, and therefore phi is actually defined over K itself. So this shows that W and W primes are isomorphic over K. So this I have been a little sketchy here, but this actually shows, this essentially shows that phi is injective. The surjectivity part we will be looking at in the next. So surjectivity, again I'll give a brief sketch of the surjectivity of this association, which we will be looking at next in next session. So I'll stop here. Yeah, there was this interruption in the internet, and it's kind of, sorry for that, but yeah, I will repeat some of these and part again in the next session.
Any questions, comments?
Yeah, so thanks Chandrakant and both the speakers.